All right, our last topic for chapter 12 is all about solids and the structures that they form. So solids form well-ordered structural arrangements that we refer to as crystals. And within these arrangements, we can find repeating patterns in the lattice of the crystal, and we call those repeating patterns the unit cell. Okay, so if I have a nice orderly arrangement of atoms here, then the unit cell will be connecting the centers of each of those spheres. Now remember, this is three-dimensional. So what I've done here is I've pulled an image from Chem115 that shows the three main types of unit cells that you can find. So the first one on the upper left here is the simple cubic. So the arrangement here would be two-dimensional, and then if we add three-dimensional, then we get a cube. Okay, so remember, all of these things are three-dimensional. It's very important to keep that in mind. All right, now the simplest is the simple cubic. Okay, and it's just 4 atoms on each of the corners of the spheres. I guess that would be 8 atoms on each of the corners of the spheres. Right, so in 3 dimensions, we get 8 corners, and there's 1/8 of an atom on each corner. Atoms per corner. Right, so total in the simple cubic, we have 1 atom per cell. Okay, so if we look at our three-dimensional drawing here, right, we have 8 corners, and each corner has 1/8 of an atom. So we get a total of 1 full atom in a unit cell. Right, now we'll come back to this in just a moment, but we want to talk about some basic characteristics of unit cells. Characteristics of unit cells. All right, the first is coordination number. Right, and the coordination number tells us how many atoms touch one atom in the lattice. Okay, so if we were thinking about our primitive cubic or our simple cubic, right? Let's pick. Well, it's kind of hard to do in this drawing, but let's pick this one right here. Right, so we can think about it. If I have something like this, and if I'm wanting to find out how many atoms touch one, how many atoms touch this one, right? So in 2 dimensions, I can think about this one touches, this one touches, this one touches, and this one touches. But we also have to think 3-dimensional, so in front and back as well. So for simple cubic, okay, there are 6 atoms touching. Right, so our coordination number for simple cubic is 6. Right, so we have to think in 3 dimensions and think about how many atoms will touch one atom in that lattice. Okay, and it'll be different for each of the arrangements. So our next important characteristic are the number of atoms in the cell. Okay, so simple cubic has 1. Now the third main characteristic is cell edge length and cell volume. Okay, so again, sticking with the simple cubic, if I'm looking at my unit cell, right? Each one of these pieces is a radius, right? Because I'm imagining that this is a sphere, right? So my edge cell length in this case will be 2 times r, 2 times the atomic radius, right? And so my volume is just height, width times length times height. So the volume will just be 2r cubed. Okay, and this will be slightly different for the other unit cells. We'll talk about those in turn in just a moment. Right, and then our next and last characteristic is packing efficiency. Okay, talking about void space. Right, so there's a way for us to calculate packing efficiency. You won't really need to know this necessarily because packing efficiency will be provided for you depending on the unit cell. But to let you know how they figure it out, so they calculate percent occupied, and that's the volume of the spheres in the cell divided by the volume of the cell times 100. Right, so for simple cubic, we have one sphere, so 1 atom per unit cell. Right, so we get 1 times the volume of the sphere, 4/3 pi r cubed, divided by the volume of the cell, which is 2r cubed. The r's cancel out, so we get a packing efficiency of 52.3%. Right, so primitive or simple cubic leaves a lot of empty space. All right, so let's come back and talk about these various characteristics for our other arrangements, right? So the next most complicated is the body-centered cubic. Okay, so we have one whole atom in the center of that unit cell, and then each of the 8 corners has 1/8 of an atom. So for body-centered cubic, we get 2 atoms per cell. Right, now our edge cell length, we can do some wonderful geometry involved, and it's always fun for me to try and teach that geometry because it's all about triangles, right? But we can take a triangle that goes along one edge, through the center, and we relate it all to atomic radius. But we're going to sort of skip over that and say that the edge cell length is equal to 4r over the square root of 3. Okay, and the volume, okay, 4 over the square root of 3 is just 2.31. So the volume will be 2.31 r cubed. All right, and our coordination number will be 8. And we don't really need to worry about that too much. Let's see, I'm kind of out of room here. I'm going to remove this a little bit. Okay, and for the body-centered cubic, our packing efficiency will be 68%. All right, now our face-centered cubic, let's take a look at that one. So our face-centered cubic has half of an atom on each of the 6 faces of the cube. Right, so half an atom times 6 faces, that gives us 3 atoms total for the faces. And then we again have 1/8 of an atom on each of 8 corners. So the face-centered cube has 4 atoms per cell. Right, it has a coordination number of 12, and our edge is square root of 8 times r. Right, so our volume is 2.83 r cubed. And our packing efficiency is 73.9. Okay, so all of this information will be given to you on an exam. Okay, so the other thing to understand about face-centered cubic is that there are 2 different arrangements for face-centered cubic. They both result in the same unit cell, but you'll see face-centered cubic referred to as either hexagonal, close pack, or cubic close pack. Okay, and all that is referring to is how the different layers of the arrangement are stacked with each other. But they both result in the same unit cell of face-centered cubic. Right, so the most important stuff for you to have in your usefulness is right here. Okay. All right, so let's work a problem. All right, so our example problem for this section starts like this. So polonium is simple cubic with a density of 9.169 grams per cubic centimeter. What is the atomic radius? And volume of the unit cell? Okay, so that's really not much information for us to go on. All we're really given is the density and the fact that it's simple cubic. But we have some useful information just from that. Okay, so the simple cubic has 1 atom per unit cell. Okay, and we know the volume of that cell is 2r cubed. All right. We also know volume of a sphere 4/3 pi r cubed. And what we need, so with that information, what we need is the volume of one atom. Okay, so our density has grams per volume, right? So what we want is volume per atom, right? So let's see if we can take our density and rearrange it so that we find out what is the volume of one atom of polonium, right? So we want centimeters cubed over atoms. So let's see if we can accomplish that. So let's start with our density, 9.169 grams per cubic centimeter. Right, so this is grams of polonium per cubic centimeter. So we want to get to atoms. So we already know how to go from grams to atoms of an element. We learned that back in one of our earlier chapters. So I'm going to go moles over the molar mass of 2.209 grams of polonium per mole. Right, so now I have moles per cubic centimeter, and I'm going to use Avogadro to get to atoms per cubic centimeter. Right, so what I end up with, 2.642 times 10 to the 22 atoms per cubic centimeter. Right? But I need centimeters cubed per atom. Right? So what I'm going to do is take the inverse of this number. Right? So if I just take 1 over that 2.642 times 10 to the minus 22, what I get is for every 1 centimeter cubed, .642 times 10 to the 22 atoms equals 3.785 times 10 to the minus 23 cubic centimeters per atom. Right, so this is my volume of one atom. Right, and we're treating these as spheres, right? So if I know the volume of a sphere, I can solve for the radius. Four-thirds pi r cubed equals 3.785 times 10 to the minus 23 cubic centimeters. So do a little rearranging. So R equals divided by 4/3 pi, and that's all cubed root. So we'll find that our radius, 2.08 times 10 to the minus 18 centimeters, and we convert that to a slightly more usable unit, or 208 picometers. Right, so this is our atomic radius of polonium. So that's one half of our question answered. So the next question was the volume of the cell. And for simple cubic was 2r cubed. So 2 times 208 picometers cubed. Gives us the volume of the unit cell as 7.12 times 10 to the 7 cubic picometers. All right, so just a few simple pieces of information can take us very far with the knowledge that we have of geometry and of edge cell length and volume and spheres and all that wonderful stuff. All right, now that does it for our Chapter 12 material. There are other topics in the chapter pertaining to polymers and superconductors and semiconductors and all that wonderful stuff, and we're not going to cover it. We are out of time, so we're going to stop right here with Chapter 12, and I hope you've enjoyed.